Hi everyone, for this video I'm going to show you some of the examples on how to use the Fourier Transform properties based on the table given in the list of formulas. Form of the following signal, given that ft is equal to exponent negative 2 t minus 1 multiplied by unit step function t minus 1. So basically this is an exponent function which has been time shifted. So you find in the table the pair of Fourier transform for the exponent function as well as for the time shifting properties. It is found out that for exponent function, the pair is a divided by a plus j omega, and for the time shifting properties, the pair is f t minus t naught. Okay, it will become f omega, which is the Fourier transform for this ft, and then you have to multiply the f omega with exponent negative j omega t naught. Okay, so mesh with the equation here. Capital A is equal to 1, small a is equal to 2, and t naught here is the time shifting, which is equal to 1. So from here we can find that f omega is equal to, okay, this f omega is equal to, a is equal to 1, so 1 divided by small a is 2 plus j omega. Okay, and then you have to multiply by exponent negative j omega t naught. So you just multiply by exponent negative j. So this is the answer for exercise 1 for this first question. As simple as that. Okay, the next example, still using the time properties. Find the Fourier transform of the following signal. So for the first question here, given that g1t is equal to exponent negative 2 tut. So this is a straightforward question, and in which this is the exponent function. So you find from the table the pair for exponent function multiplied by unit step function is a divided by a plus j omega. Okay, so from here we can get that g1 omega is equal to 1 divided by 2 plus j omega. Okay, because capital A here is 1 and small a here is 2. Okay, and then based on this question, based on this answer, so we need to find out the Fourier transform for the new function, which is g2t equal to g1 3t minus 7. So basically for this question, this is a g1 function which has been time transformed. Okay, so you use the time transformation properties from the table, which is f a t minus t naught. Okay, and the Fourier pair here is 1 over magnitude a f omega divided by a multiplied by exponent negative j omega t naught divided by small a. Okay, so we know that g1 omega, okay, for this example, f here is actually g1. Okay, so now what we can do now here is we use this answer here. Okay, so g2 omega is actually f, the Fourier transform for g2t. This is how you write the answer, which is Fourier transform for g1 3t minus 7. Okay, so from here we know that a is 3, okay, when you mesh with this, and t naught is 7. Okay, so we can get that g2 omega is equal to 1 divided by 3. Why 3? Because we use the transformation properties. So divide by a. So a is 3. G omega divided by 3 multiplied by exponent negative j omega, and t naught here is 7 divided by 3. Okay, so you cannot just leave it like this. You have to put omega over 3 inside this g1. Okay, so basically your answer here is 1 divided by 3, and g1 here is 1 divided by 2 j omega. So 1 divided by 2 plus j, and this omega you substitute by omega over 3. So omega over 3 and multiply by exponent negative j omega 7 over 3. Okay, and basically this omega you don't have to change to omega over 3, because you just have to change omega over 3 or divide by 3 only for g1 omega. Okay, because g2 omega is based on the Fourier transform for g1, which has been time transformed. Okay, so basically this is g1. Okay, so this is the answer for question 1. Okay, and also question 2. For exercise 3, still on time transformation. So the question is, given that Fourier transform for xt is xj omega, find the Fourier transform for first function is x1t, which is based on the xt here, that has been time transformed. This one is time shifted and also time reversal. And for question 2 is x2t, which has been time transformed based on this xt. So now the Fourier transform for xt is already given, which is xj omega. Okay, so to solve for this, we solve one by one. For the first function is x1 minus t. For the first question, x1t, here you use the time transformation properties. So from the table, f at minus t naught will give the Fourier transform pairs of 1 divided by a, f omega divided by a, exponent negative j omega t naught divided by a. Okay, so first we solve for this one, x1 minus t, x1 minus t, rearrange back so that it will become x negative t plus 1. So from here you can see and mesh with this form. Okay, and a here will be negative 1 and t naught here is negative 1. Okay, so you put this in the formula here, and f omega over a you take based on the given Fourier transform, which is xj omega. Okay, so for x negative t plus 1, the Fourier transform here is x negative j omega exponent negative j omega multiplied by 1. So how did I get this? Okay, first we already know that small a here is negative 1. So 1 divided by the modulus for this is 1 as well. So and then f omega divided by a is actually from here. So xj omega here should be negative, because omega divided by a here and a here is negative 1, should be negative omega. So here we put x negative j omega and then multiply by exponent negative j omega t naught divided by a. So t naught here is negative 1 and a here is negative 1. So it will become 1 here. So negative j omega. So for the first part, the Fourier transform here is x negative j omega exponent negative j omega. For the second part, we rearrange so that negative t is on the left side. So negative t, negative 1. So from here, you identify that a is equal to negative 1 and t naught is equal to 1. Okay, so straight away you use this formula. Okay, and then this is for Fourier transform. You will get x negative j omega. J omega, and for this one is exponent j omega. Okay, because the formula here is negative j omega and then multiply by t naught, and for this part t naught here is 1 and then divide by a, which is negative 1. So it become the division here will become negative 1 multiplied by negative here, it will become exponent j omega. Okay, so from here x1 omega is the summation of this part and also this part. Okay, so x negative j omega multiplied by exponent j omega plus x negative j omega exponent negative j omega. Okay, so we can further rearrange this one. Okay, we can take out the 2 the x negative j omega. Okay, so we take out the x negative j omega so that we can put in the bracket here exponent j omega plus exponent negative j omega. Okay, here you can further simplify so that it will become cosine function, because this is a two exponent function with the opposite sign. Okay, so here we can put divide by 2, and then we can add 2 here. Okay, so that this one will become 2 x negative j omega cos omega. So this is okay, 2x negative j omega cos omega. Okay, and here for the question 2, again you use the time transformation formula, which is this. Okay, so we can get here small a here is 3 and t naught here is 6. Okay, so for x2 omega, this one is 1 divided by a, so 1 divided by 3 x, and because f omega divided by a is actually xj omega. Okay, so xj omega divided by a, which is 3, multiply back by exponent negative j omega, and t naught here is 6 divided by 3. Okay, so here we get 1 divided by 3, and xj omega 3. Okay, xj omega 3 here is basically, okay, so however I want to put exponent function here at this part, so become exponent negative j omega 2. Okay, so exponent negative j 2 omega, sorry for the bad handwriting, x j omega divided by 3. Okay, so this is the answer for question 2. Okay, now for exercise 4, use the superposition theorem together with Fourier transform pairs to obtain Fourier transform for the signal shown. So this signal is based on the superposition of two rectangle signals. Okay, so in order for you to find the Fourier transform for this signal, you need to find the equation for this individual triangle. Okay, so we need to recall back the original rectangular signal, which is given by the shape like this. Okay, in which this one is negative tau over 2, tau over until tau over 2. Okay, and the amplitude here is a, and the duration here is tau. Okay, so for this rectangle, the equation here is a rectangle t over tau. Okay, and then based on this first rectangle, we can derive the equation here. So let's say I put this as x1t, and this second rectangle as x2t. So x1t is actually a rectangle which has been shifted by, you see like this, by negative 3 over 2, which is 1 over 5, or 1.5. negative 1. Okay, and this one has been shifted by from the origin. Okay, because we are talking about a rectangle signal from the original form, which is from the origin. So this one has been shifted by 1.5. Okay, so we can say that x1t is rectangle t, because this one has been shifted to the left, so this one is t plus 1.5. And then for x2t, this is a rectangle t minus 1.5, which is the rectangle signal that has been shifted by 1.5 to the right. Okay, and from the table, we know that from the table given in the list of formula, a rectangle t over tau will give you the Fourier transform of a tau sinc omega tau over 2. Okay, and then because of this time properties, you will need to use the time properties as well. So this one is f t minus t naught. Okay, and the Fourier transform here is f omega exponent negative j omega t naught. Right. So based on this, we can find the first Fourier transform for x1t. So x1 omega is equal to, for this case, for the first case here, a is 1 and tau is 1 as well. So a tau is equal to 1, so you can just put like sinc and omega divided by 2 because tau is 1, and then we can multiply straight with this exponent negative j omega, and for the first x1 t naught here is negative 1.5. Okay, so this one will become sinc omega over 2 exponent j omega 1.5. Okay, for the second one, x2 omega. Okay, again we can get sinc omega divided by 2 exponent negative j omega multiplied by 1.5, so negative j omega 1.5. Okay, because the t naught here is 1.5. Okay, so from here we can get x omega equal to x1 omega plus x2 omega. So this is the superposition theorems. Okay, where you can get the individual Fourier transform for each rectangle here, then you can add together. So this one is sinc omega over 2 exponent j omega 1.5 plus sinc omega over 2 exponent negative j omega 1.5. Okay, so from here you can take out the sinc omega divided by 2. Okay, and this one will become exponent j omega 1.5 plus exponent negative j omega 1.5. Okay, so from here, because of this, you can see that it is similar to the Euler's theorem. Okay, so you can make it in terms of cosine function. So you can multiply by 2 divided by 2. Okay, basically you multiply by 1. Okay, so here you can solve for this. Will become 2 sinc omega divided by 2, and this one, because this is the summation of exponent function with opposite sign, and divide by 2, so this one will become cos 3 omega divided by 2. Okay, so this is the answer for exercise 4. For exercise 5, now we try to do time transformation and also differentiation. Given that Fourier transform for signal gt is g omega is equal to 1 squared divided by omega squared plus j to omega plus 4. So basically you don't have to find the Fourier transform for signal gt because it is given. So by using the Fourier transform table, determine the Fourier transform for the following function. Okay, for the first one is g1t is equal to 2g minus t. So this is basically g1. Okay, this one is basically based on this gt, which has been time reversal and also multiplied by 2. Okay, so for the solution, you use the time reversal properties. Here, 2g negative t. Okay, the Fourier transform pairs or Fourier transform for this is 2g negative omega. Okay, and from here we can solve that g1 omega is equal to g omega is known here, so basically you multiply the whole equation here by 2. So 2, and then here is 1 plus omega squared. Basically you change omega squared to negative omega squared. Okay, so whatever omega here, you change to negative omega. So divide by negative omega squared plus j to negative omega plus 4. Okay, and then this one will become 1 plus omega squared minus 2j omega plus 4. So just like that, you don't have to further simplify this equation. Okay, and then for the question 2 here, g2t is equal to g2t plus 6. Okay, so for the second g function here, again based on the original signal gt here, and you use the time transformation, okay, which is given as from the table f(at) minus t naught. The Fourier transform here is 1 divided by a f omega divided by A exponent negative J omega T naught divided by A. Okay, so for T naught here is equal to negative 6 and A here is 2. Okay, basically you mesh with this equation. And then from here you can get G2 omega equal to 1 divided by 2 G omega divided by 2 multiplied by exponent negative J omega T naught here is 6. Okay, divide by 2. Sorry, T naught here is negative 6. Okay, divide by 2. So for this omega, you don't have to change it to omega over 2. Okay, only whatever in the bracket here. Okay, and then you solve for this. This one is 0.5 G omega divided by 2 exponent J3 omega. Okay, so you take the G omega from here, 0.51 plus, okay, so omega squared you change to omega over 2 squared. So it will become omega squared over 4 and divide by omega squared over 4 plus J 2 multiplied by omega over 2 will become J omega. Okay, and then plus 4 multiply back by exponent J3 omega. So again, this is the only answer. You don't have to further simplify this equation. Now for the third question, you need to use the differentiation properties to solve for this. Okay, so I'm going to solve in the next page. Okay, using the Fourier Transform properties for d3 dt3, okay, we can see that n equal to 3. Okay, so for the Fourier Transform pairs here, you should use the differentiation properties, which is j omega order of n g omega. Okay, so from here you can solve for g3 omega, which is equivalent to j omega power of 3 g omega, and g omega here is given, so j omega, okay, power of 3 1 plus omega squared divided by omega squared plus 2j omega plus 4. Okay, so that's it for question 3. Okay, so you do not have to further simplify this equation. 7, we are going to use the duality properties. Okay, given that ht is equal to sinc t, by using duality of Fourier transform, determine h omega. Okay, so now we know that for duality, based on the table, is given as ft. The Fourier transform is 2 pi f negative omega. Okay, so from the table we see that we will see that for sinc function, it will be in Fourier transform domain or frequency domain, in which the pair of this function sinc is rectangle function. Okay, in other words, you will find from the table that rectangle function in time domain will give you the sinc function in Fourier transform domain. Okay, so remember that. Okay, from the table, a rectangle t divided by tau. Okay, the pair of Fourier transform here is a tau sinc omega tau over 2. However, this is based on the omega, which is the frequency domain of Fourier transform domain. Okay, so from here you rearrange so that it become a tau sinc. It means that you convert this or change this Fourier transform domain into t domain. So a tau sinc, just change omega with t tau over 2. Okay, and the Fourier transform here should be 2 multiplied by pi and f negative omega. So this one should be f negative omega you will take from the time domain function. So a rectangle t you replace with negative omega, so negative omega over tau. Okay, and since for rectangle function it is based on the origin is 0, so basically it is symmetry. So we can ignore the negative here. So basically it can become positive. Okay, so from here, sinc t, okay, is a tau sinc t tau over 2. Okay, and you find out the value for a and also for tau. So we know that a tau here is equal to 1. Okay, because there's no numbers before seeing here. So a tau is equal to 1. So a here will become 1 over tau. And tau here, okay, the tau here is actually 2. Okay, because 2 divided by 2 is 1. So tau is 2. So this one should be 1 divided by 1 divided by 2, which is 0.5. So from here we can find the answer for h omega. So h omega here is 2 pi multiplied by a, which is 0.5, and then rectangle omega divided by 2. Okay, so 2 multiplied by 0.5 is 1. So this one is actually pi rectangle omega divided by 2. Okay, so this is the answer for sinc t. Okay, the Fourier transform for sinc t, the answer is rectangular. So this is what we call, or this is what we meant by duality properties. Right? So for exercise 8 here, we're going to use the convolution properties, and this is a bit of application. A system is given by an input of xt and the output of yt as shown in the figure 1. So I hope you already understand the convolution process, which you have watched the video from chapter 1 with the convolution in time domain. So now we are going to solve the convolution in frequency domain, which is using the Fourier transform properties. So given gt here is as in the figure here, which is the rectangular function, find the Fourier transform of the output yt. Okay, so we know that xt here will convolve with ht in time domain. Okay, however, for the frequency domain, it will become multiplication. Okay, x omega will multiply by h omega. However, this question is not straightforward because we need to find the Fourier transform for xt first, okay, which is based on gt signal, and then ht, which is also based on gt signal. So we need to derive the function gt in terms of time domain. So if we see this, gt is basically a rectangle function, okay, from the original rectangle function. So from here we can say that gt is rectangle t over tau. Okay, and then we will get the Fourier transform, which is g omega equal to tau sinc omega tau over 2. Okay, so I hope by now you already know how to obtain the Fourier transform for the rectangle function. Okay, so this is a straightforward where you can find the pairs here from the table. Okay, and xt here is equal to 5g to t. Okay, and based on the time transformation from the table, we can use that properties gat, and the Fourier transform here is 1 divided by a, g omega divided by a. So from here we can say that for xt here, a is equal to 2. Okay, so a equal to 2 applies for ht as well. Okay, so from here we can find that x omega is equal to 5 multiplied by 1 over 2 g omega divided by 2. Okay, so why 5 here? Because x omega is 5 multiplied by g to t. Okay, so g to t, we just use this formula. So a equal to 2, so this one is 1. Sorry, this one should divide by a, so divide by 2, g omega divided by 2. Okay, so from here, you can further solve this. This one will become 5 divided by 2. Okay, tau, sinc, and omega here you change to omega over 2. So this one will become omega tau over 4. Here this is x omega, and for h omega, it is based on ht equal to 2g2t. Okay, so for h omega, this one is 2, 1 multiplied by 1 divided by 2, g omega divided by 2. Okay, so basically you use this g omega again. Okay, from here you cancel out the 2, so this one will become tau sinc omega tau over 4. Okay, so from here we can use the multiplication properties for the convolution. Y omega equal to x omega multiplied by h omega. Okay, so basically this is quite a simple process compared to when you use the convolution in time domain. Okay, so this one equal to 5 divided by 2 tau sinc omega tau over 4 multiplied by this one tau sinc omega tau divided by 4. Okay, and then solve for this. We will get 5 tau squared divided by 2 sinc squared omega tau divided by 4. Okay, so this is the answer for y omega. Okay, again the question here asks you to find the Fourier transform of the output yt, which is y omega. So in order to solve for this, we need to find the x omega first, which is based on the gt, and also h omega, which is based on the gt as well. So in order to get x omega and h omega, you need to find g omega first. And in order to find the g omega, you need to find the rectangle function in time domain. Then only you can use these steps to get the y omega. Okay, so I think that's all the video tutorial for Fourier transform properties. Okay, so I hope you can try to do the tutorials that I have uploaded on the e-learning. So until the next video, thank you very much.